ak be equal to a real part plus a imaginary part, okay? So in this case, x of t will be equal to a0 plus 2 times summation, okay, from 1 to infinity, okay? Summation, 1 to infinity, the real part of ak times e to the jk omega naught t, okay? So ak is bk plus jck, and e to the jk omega naught t is cosine plus j sine, okay? So if you take only the real part, then what you have remaining from this multiplication is the real part times the real part minus the imaginary part times the imaginary part, okay? So this gives you bk cosine k omega naught t minus ck sine k omega naught t. Okay? Right, so this is what we get at the end. Okay? Now, in the previous example, here, all of the Fourier series coefficients ak are actually real, right? All of these are real. So when all of them are real, this means that, when you write ak in terms of its rectangular form, the ck's are real. The ck's are 0, so this term goes away. So what you have is just the summation of these cosine functions with 0 phase, okay? And you can check that this is indeed the form, okay? Okay. So in example 3.2, we have ak that is real, or in other words, ak equal to bk, and therefore x of t is simply a0 plus 2 times summation k from 1 to infinity. Let's just write it as ak cosine k omega naught t. Okay? Okay. So this is just a side note to let you know that in some textbooks or in some papers that you may encounter, you will see people writing the Fourier series representation in these forms instead of in terms of the complex exponential. And this is because, right, in those contexts, they are focusing on x of t that is real. Okay? But for you, I would still suggest that you focus, for us, we would want to focus on the more general form, right, using these complex exponentials. Okay? Okay. So in this example here, right, we're trying to visualize that, if you take the superposition of more and more complex exponentials, you will be able to construct these periodic waveforms of arbitrary shape. Okay, so you can construct more and more complicated signals or signals of various types by combining more and more of these complex exponential terms. Okay. But if you go the other way around, right, suppose that you start out with a certain signal x of t, right? Suppose that you are given a periodic signal. Suppose that you are given a periodic signal x of t, and you know that its Fourier series representation exists, then how do you find this expression, right? Or in other words, how do you find the values of these coefficients that allow you to construct this signal x of t that you are given? Okay? So suppose I give you a signal x of t. How do we know how to write it in terms of this Fourier series representation? Okay. Now, one simple way is to try to see if you can directly decompose it into a sum of complex exponentials. Okay? So as the example here, right, suppose that if x of t is this sine function, then by Euler's formula, right, by Euler's relation, we know that we can write this as 1 over 2j e to the j omega naught t minus 1 over 2j e to the minus j omega naught t. Okay? So if x of t is just this sinusoid here, directly by Euler's relation, we know how to write it, decompose it into the superposition of these complex exponentials. Okay? So in this case, we immediately know what are the Fourier series coefficients. Right? So this is the coefficient corresponding to the term k equal to 1, and this is the coefficient corresponding to the term k equal to minus 1. Okay? So in this case, A1 is 1 over 2j. A minus 1 is minus 1 over 2j. And all the other terms are 0. Okay, for all k not equal to plus or minus 1. Okay. Now, you can do the same for this example as well, right? Because in this example, x of t is just a superposition of these sine and cosine functions, okay? And for each one of these, right, by Euler's relation, I can decompose into the sum of complex exponentials, okay? So if I do that, then this is equal to 1 plus, okay, so this is 1 over 2j. This term is the same as the example above. Okay. So for the second term, we have e to the j omega naught t plus e to the minus j omega naught t. And for the third term, we have 1/2 e to the j 2 omega naught t plus pi over 4 plus e to the minus j 2 omega naught t plus pi over 4. Okay. Okay. So for the sine function, I can split into 1 over 2j exponential of this j of this term here minus e to the minus j of this term, okay? And for cosines, I can write as 1/2 of e to the j omega naught t plus e to the minus j omega naught t. The 1/2 cancels out with the 2, so this is what we have left. And for the third term, we have 1/2 of e to the j of this term plus e to the minus j of the same term. Okay? So by Euler's relation, we directly split this into the superposition of these complex exponentials. Okay? So this is the term corresponding to k equal to 1. So is this. This is the term corresponding to k equal to minus 1. All right, this is a term corresponding to k equal to 2, and the term corresponding to term k equal to minus 2. Okay? So immediately, by observing this formula, you find that A0 is 1. A1 is 1 over 2j plus 1. Right? A1 corresponds to the term e to the j omega naught t, right, which is this term and this term. So the coefficient is 1 over 2j plus 1. Okay? Now, it's often more intuitive to write this j in the numerator instead. Right? So in that case, you get 1 minus 1/2 j. Okay? So you get this by just multiplying j to both the numerator and denominator. Okay. So similarly, you can get a sub minus 1 as 1 over 2j. I'm sorry, minus 1 over 2j plus 1, or 1 plus 1 plus 1/2 j. Okay. So for a sub minus 1, right, this corresponds to the coefficients of e to the minus j omega naught t. Okay? So this is minus 1 over 2j plus 1, which is 1 plus 1/2 j. Okay. Now for a sub minus 1, you can actually obtain it much easier by just taking the complex conjugate of a1. Because x of t is real, therefore the Fourier series coefficient must be conjugate symmetric. Okay, so this is what we just showed up here. Okay. All right. So continuing in this fashion, you can find A2. Right, A2 is the coefficient corresponding to e to the j2 omega naught t. Okay, so the coefficient should be 1/2 times e to the j pi over 4. Okay. So this is 1/2 e to the j pi over 4. Okay. Now, by Euler's relation, you can write this as cosine pi over 4, which is 1 over square root 2, plus j sine pi over 4, which is again 1 over square root 2. Okay? So this becomes square root 2 over 4, 1 plus j. Okay. And for a sub minus 2, okay, you could have obtained the coefficient by observing this term here, but you also could have obtained it by taking the complex conjugate of A2. Okay, so this will give you square root 2 over 4, 1 minus j. Okay, and ak is 0 for all k otherwise. Right, so all k not equal to 0, plus minus 1, plus minus 2. Okay? All right, so do you have any questions about this? Okay.这部分有没有什么问题 ？OK。Right， 所以我们这里的目标就是希望说，我现在如果给你一个 periodic signal x of t， 我怎么样找到它的 Fourier series representation？OK， 所以这里这就等效于说我们怎么样去找到这一组的 coefficient ak？OK，so one way to do this is by direct observation. Right, so if you have a signal that you can easily write out as a linear combination of these complex exponentials, then just by observing the values that you have in front of these complex exponentials, you can directly find these coefficients. Okay. But obviously, this is not the case for most other signals, right? So for more general forms of x of t, we need to have a more systematic approach to help us find these coefficients. Okay? And the way we do this is as follows. Okay? So we need to find a procedure to find these coefficients. Okay? So the way we do this is as follows. So suppose we want to find the coefficient an. Okay? Then what we do is that we take the integral of x of t times e to the minus j n omega naught t dt over t from 0 up to capital T. Okay? So let's see what happens when we take the integral of x of t times e to the minus j n omega naught t. Okay. Now notice that for an, right, for an, it corresponds to the complex exponential e to the j n omega naught t, right? So if you're looking at an, its complex exponential is e to the j n omega naught t. But here we're multiplying x of t with e to the j n omega naught t with a negative sign there, right? So we're basically taking the complex conjugate of the complex exponential corresponding to an. Okay? All right, so let's see what happens here. All right, so let's just substitute x of t inside. So in this case, we get integral summation ak, k from minus infinity to infinity, e to the j k omega naught t times e to the minus j n omega naught t dt. Okay? Now let's combine the two exponential terms. Right, I can bring this summation outside. Integral of e to the j k minus n omega naught t dt. Okay. Now let's look more carefully at this integral here. Okay. So for this integral, this is integral 0 to t e to the j k minus n omega naught t dt. Okay. Now, what is this complex exponential, right? It is basically a cosine in the real part and a sine in the imaginary part. So if you write this out, you have the integral of the real part, which is cosine k minus n omega naught t dt, plus the integral of the imaginary part, which is sine k minus n omega naught t dt. Okay. All right. Now, when k is equal to n, okay? So when k is equal to n, cosine 0 is 1, right? So this integrates to capital T, and sine 0 is 0, so the imaginary term is just 0, okay? So this integrates to capital T when k is equal to n. Okay. Now, if k is not equal to n, right? K minus n is some integer multiple of omega naught. Okay. So for any sinusoid that is an integer multiple of omega naught, this sinusoid is still periodic with period capital T. Okay? So when we integrate from 0 to capital T, we are integrating over integer periods, right? Integer periods of this sinusoid. Okay? So whenever we integrate over entire periods of a sinusoid, this integral should be 0, right? So suppose that this is capital T, right? And you have a sinusoid like this, okay? Right, certainly this extends further, okay? But suppose you're just looking at 0 to capital T. When 0 to capital T contains, full periods of the sinusoid, when you integrate over this, you have positive parts that cancel out with the negative parts. And again, positive parts canceling out with the negative part, okay? So the integral of sinusoids over entire periods should be equal to 0. And this is the same for both cosine and sine, okay? So this is 0 when k is not equal to n, okay? So if you substitute this inside, right, among the summation over all k, this term is non-zero only when k is equal to n. And in that case, this integral is capital T. So this is equal to an times t. Okay? So therefore, how do you find the coefficient an? Right? You just move capital T to the other side. Right? So you take 1 over t, the integral of x of t times e to the minus j n omega naught t for t from 0 up to capital T.